Welcome to our next lecture in statistics at Dallas College, specifically Math 1342 with Professor Michael Bailey using the ALEX system. In this section, 5.2, we're looking at binomial variables and calculating binomial probabilities. A binomial distribution is when you have two terms. So let's look at an example. Your favorite restaurant is giving away a coupon with every purchase of a meal. 20% of the coupons entitle you to a free milkshake, and the rest of them say, better luck next time. Suppose that 10 of you order lunch at this restaurant. What is the probability that 3 of you will win a free milkshake? This is an example of a binomial probability. And it's not a very straightforward probability, but it's one of the most powerful in statistics. Its value depends on the fact that there are 10 different ways to get let me say that again. Its value depends on the fact that there are different ways, not just 10, potentially, to get 3 winners from a group of 10. And you remember this before about counting. In general, if we let x be the number of people out of 10 that win a free milkshake, we will learn that x has a distribution called the binomial distribution, which is one of the most useful probability distributions. In the example we just talked about, each time we examine a coupon, we call it a trial, or like an experiment. So there are 10 trials. When a coupon is good for a free milkshake, we call it a success. The random variable x represents the number of successes in 10 trials. So of course we could go from 0 to 10 possibilities for the number of successes. A random variable that represents the number of successes in a series of trials has a probability distribution called the binomial distribution. The conditions are that you conduct a fixed number of trials. There are 2 possible outcomes for each trial. One is labeled success and the other would be labeled failure. The probability of success is the same for each trial. This is a requirement for a binomial distribution. And the trials are independent. This means that the outcome of one trial does not affect the outcomes of the other trials. And the random variable x represents the number of successes that occur. So all of these have to be true for it to be a binomial distribution. So see if you can think about each of these cases and determine whether it's a binomial variable. Hit pause now and try. A coin is tossed 10 times. Let x be the number of times the coin lands on heads. This is a binomial experiment. We've got a fixed number of tosses. Each toss of the coin is a trial. There are 2 possible outcomes, heads or tails. Since x represents the number of heads, heads would be counted as a success, and the trials are independent. That means that each time you flip the coin, you have the equal likelihood or equal probability of success. 5 basketball players each attempt a free throw. Let x be the number of free throws made. This is not a binomial experiment, mainly because the probability of success is not constant. It varies depending upon the level of skill of each of the players. So it's not an equal playing field, so to speak. 10 cards are in a box. 5 are red and 5 are green. 3 of the cards are drawn at random. Let x be the number of red cards drawn. This is not a binomial experiment because the trials are not independent. As soon as you pull a card out, notice that you have fewer cards in the box, and so the probabilities will shift as well. And again, I just want to remind you of those. So for a binomial distribution, there's a fixed number of trials. Two possible outcomes, one is success, the other is failure. The probability of success is the same on each trial. The trials are independent, meaning that the outcomes of one trial does not affect the outcomes of the other, and the random variable represents the number of successes. So let's try some more of these. Decide in each case whether x is a binomial random variable. A fair die is rolled 20 times. Let x be the number of times the die comes up 6. This is indeed a binomial random variable, okay? Because we have a specific outcome that has the same probability each time that we're rolling the die. And notice it says a fair die. A standard deck of 52 cards contains 4 aces. 4 cards are dealt without replacement from this deck. Let x be the number that are aces. Now, you remember, without replacement means you don't put the card back in the deck. So, of course, because we don't put the card back in the deck, we have a different probability each time. For example, if we drew an ace on the first time, we would have fewer aces to draw from in subsequent drawings. A simple random sample of 50 voters is drawn from the residents in a large city. Let x be the number who plan to vote for a proposition to increase spending on public schools. This again is a binomial because you have a probability based on the percentage of people that are likely to vote, and each selection is independent of the other because one person is likely to vote doesn't impact the next one. Now let's look at how we figure out a probability, and this can be a little bit confusing. Consider an experiment of tossing 3 times a bias coin. This is no longer a fair coin, and this coin has a probability of 0.6 of coming up heads, so it's more likely to come up heads than tails. X is the number of heads that come up. If we want to compute the P of 2, this is the probability that exactly 2 of the tosses are heads. If we go through our tree diagram, we can find out there are 3 possible arrangements of 2 heads. And that is heads, heads, tails, heads, or tails, heads, heads. And this, again, we've been doing before using tree diagrams to see all the possibilities. The probability of HHT, this is just that one case, notice is the probability that we get heads on the first coin, heads on the second coin, and tails on the third, right? If we have a 0.6 probability of heads, then the rest of the probabilities that complement the probability of tails would be 0.4. Notice that all 3 of these probabilities in different order have the same probability. They just in different order, but we can multiply numbers in different orders and get the same result. So the probability of 2 heads equals the probability of heads, heads, tails, or heads, tails, heads, or tails, heads, heads, which is adding the probability of each of those. And since they're all the same, it would just be the same as multiplying by 3. Examining this, we see the number 3 represents the number of arrangement of 2 successful heads and 1 failure, tails. In general, this is the number of arrangement of x successes in n trials, or specifically, a combination of n things taken x at a time, which we saw from a prior section. The number 0.6 is the success probability p, which has an exponent of 2. This is the number of successes of x. The number 0.4 is the failure probability, or 1 minus p, which was the success probability. And this has an exponent of 1 because we're only looking for 1 failure. We have an exponent of 2 for the successes because we're looking for 2 successes and 1 failure. And that exponent there of 1 is because we're only looking for 1 case. So with what we saw in the last example, we can see that the number of successes, X represents the number of successes in N trials. So the probability of X in the last case would be the probability of 2. With the success probability P, you can see that here, the lowercase p. The failure probability is 1 minus p, we see that here. And the probability of obtaining X successes is calculated this way. The probability of X equals the combination of n things taken X at a time times p to the X power times 1 minus p to the n minus X power. If we write out the last experiment, we can see the probability of getting 2 heads in 3 tosses is C to the combination of 3 things taken 2 at a time, times the probability of heads, 0.6, to the X power, which is 2, times the probability of tails, 1 tail, 0.4, times n minus X, which is 3 minus 2, or to the power of 1. It's a little bit confusing, but use the model to figure this out. Let's try an example. Hit pause and see if you can calculate these. The Pew Research Center recently reported that approximately 30% of internet users in the United States use Pinterest. Suppose a simple random sample of 15 internet users is taken. Use the binomial probability distribution to find the following probabilities. Find each probability. Here's our formula, so you can go ahead and use that, but go ahead and try to hit pause and try to do these problems. That exactly 4 of the sampled people use Pinterest. Okay, so in this case, we're looking for the probability of 4. So our X is equal to 4. What is our N equal to? Our N is the size of their sample, so that's 15. What is our probability of success? Okay, well, 30% of internet users use Pinterest, so our lowercase p is 0.3. People that don't use it is 1 minus 0.3 or 0.7. Now we have all the variables figured out, so we can calculate this formula. So we have p to the 4 successes, or 4 people use Pinterest. The combination of 15 things, our sample, taken 4 at a time. The probability of success is 0.3 to the 4. The probability of failure is 1 minus 0.3 to the 15 minus 4. And when we do this, we would get a probability of 0.219. Your TI-84 calculator can calculate this. And you also have the formulas if you need them to figure out the combinations. As we move forward, now we have to figure out specifically what each of these probabilities means. So for example, in B, fewer than 3 means the probability of 0, 1, or 2. Okay? So this means that we have to do this probability multiple times for each of those cases. The probability of 0 people using Pinterest, 1 person using Pinterest out of 15, or 2 people. Okay? So now we're looking at the probability of 0, 1, or 2. So we're going to do this calculation for 0, for 1, and for 2. Notice the 15 doesn't change and our probabilities don't change. So you can see through here, we get the first case is 15 items taken at 0, 15 with 1 success, 1 person using it, and 15 with 2 people using Pinterest. And when we look at that, we get we get a probability of 0.127. Now let's look at C, the probability that more than 1 person uses Pinterest. Well, this is the probability of 2, 3, 4, 5, 6, 7, 8, all the way up to the probability of 15. When we have a probability like that, that's many categories versus the other side, all we have is 0 or 1, it's easier to find the probability that one or less use it and then subtract that to 1 to find the rest of the probabilities. This is the value of knowing that all the probabilities add up to 1. So if we can calculate fewer probabilities, then it's easier. So here what we're going to do is we're going to do 1 minus the probability of 0 or 1. So we have 1 minus the probability of 0, just like we had before, plus the probability of 1. And so we get 1 minus 0.035, which gives us a 0.965 probability. So the probability is pretty high that more than one person uses Pinterest, given a sample of 15. Lastly, we have find the probability that the number of people who use Pinterest is between 1 and 4 inclusive. So this is the probability of 1 plus the probability of 0. Wait, I'm sorry, no, not 0. Probability of 1, 2, 3, and 4. Inclusive means we include 1 and 4. So we're going to, again, do all of those probabilities, and evidently I ran out of space here, so you can see this worked out in the book, but it's really the same thing. We've seen all of these except for the probability of 3. We've got 1 here, we've got 2 here, we've got 4 here, and you could calculate the probability of 3. Sometimes it's really helpful to use tables, statisticians' tables. This is the binomial probability table. And notice what it does. It gives you the value of n, what's our sample size. It gives you what our number of successes are based on that sample size. And then across the top are probabilities, okay? So remember in our last probability, we had a sample size of 15, and 30% of internet users use Pinterest. So we need to find the probability that exactly 4 of the sampled people use Pinterest. I've highlighted the table here, so we go down to where x equals 4, right? Exactly 4 people. We're looking for the p of 4. And the probability of success was 0.3. So we go across the top and find the probability that matches. And here we can see that that probability is 0.219, which is the same as what we calculated. So the tables can save us a lot of time and effort, but of course, the tables aren't probably don't cover every size of sample and every probability, as you can see here. For example, if our probability was 0.35, we could do an estimate between 0.30 and 0.40 and find the mean value between these. So now we're looking to find the probability that fewer than 3 of the people use Pinterest. Again, we have our 15. So now we have our column here of probabilities. Fewer than 3 is 0, 1, 2. So again, we can see that we would add those 3 probabilities and get our value as well. All right, our final one, more than one person uses Pinterest. Again, we're going to use the complement rule instead of adding up, a bunch of numbers. 1 minus the probability of 0 or 1, and you can see those highlighted here, 0.005, and then of course we subtract that from 1 and get the same value. I wanted you to see that, and here's the last one, that there is a tool, these tables of values. A lot of people use the tables of values, and these are in your appendix of your book if you want to copy those over. Again, in your section 5.2, you do have all the technology step-by-steps, and they also have some good examples to walk you through problems. So why don't you try this problem and see if you can solve it using the table. This should be pretty straightforward. 10% of adults said they consider themselves to be gamers. 18 adults are randomly sampled. Compute the probability that exactly 3 of them consider themselves to be gamers. So again, you can see we've moved to another section of the table where n equals 18. What is our x going to be? Since we're sampling 3 of them, our x is going to be 3. So we're going to have this 4th row here. It's in blue. And we're trying to figure, and we're going to use the probability of 10%. Okay? So here's our calculation. But notice our table value gives us that as well. So let's look at some other things that we can calculate based upon the binomial distribution or a binomial random variable. If we have a binomial random variable with n trials and success probability p, then our mean of x, our mean average value of x is n times p, the probability success. The variance of x is np times 1 minus p, again where lowercase p is our probability and n is our number of trials. And this gives us the standard deviation, which is the square root of n times p times 1 minus p. So why don't you try solving this problem? Hit pause, and then when you're ready, this is pretty straightforward, so I would definitely do it. And again, I highly recommend you try these problems on your own by hitting pause, because the more active you are, the more retention you'll have when you go to do your homework and tests. The probability that a new car of a certain model will require repairs during the warranty period is 0.15. A particular dealership sells 80 such cars. Let x be the number that require repairs during the warranty period. Find the mean and standard deviation. Okay. Well, our probability is 0.15 and our sample size is 80. So the mean is really simple to calculate. It's just the product of these two. And our standard deviation is not much more difficult. It's our 80 times the probability times 1 minus the probability of 0.15, and then the square root of this, which gives us 3.194. These are pretty straightforward calculations. Here we're saying that 12 out of every 100 cars will require repairs, and that's based on a percentage. And the standard deviation measures the spread in the distribution of the number of cars that will require repairs. Here we have another example. You might go ahead and hit pause and try this one. Gregory Mendel discovered the basic laws of heredity by studying pea plants. In one experiment, he produced plants whose parent plants contain genes for both green and yellow pods. Mendel's theory states that the offspring of such parents has a probability of 0.75 of having green pods. Assume that 80 such plants are produced. Find the mean number of green pods. Well, our sample size is 80. Our probability of having green pods is 0.75, so this is a direct calculation. Find the variance of the number of plants that have green pods. Again, this is our probability times our sample size times 1 minus the probability. Again, a pretty straightforward calculation of 80 times 0.75 times 1 minus 0.75. And finally, our standard deviation is simply the square root of the variance, and so we get 3.873. So we've covered all of these things. You should know how to determine whether a random variable is binomial based upon those conditions that we talked about, the 5 conditions. The notation for a binomial experiment, this is the combination notation. How to determine the probability distribution of a binomial random variable. How to compute binomial probabilities, and how to compute the mean and variance of a binomial random variable.